San Francisco's Bay Bridge opened in 1936, proving wrong all those who said the bay was too wide and deep to bridge. Spanning 8¼ miles, it's an impressive feat of engineering. Its design includes a lot of triangles. Structures that must be strong and stable, such as bridges, often rely on an underlying triangular framework, since triangles with fixed-length sides have stable shapes. All triangles can be classified by their sides and angles. One type is a right triangle, any triangle in which one angle measures 90 degrees. The longest side of a right triangle is the hypotenuse, which is always opposite the 90-degree angle, the largest of the three angles. If the other sides have unequal lengths, the longer one is opposite the larger of the other two angles. So, the shortest side is the side opposite the smallest angle. The sides of a right triangle are often labeled A, B, and C, with C typically used to label the hypotenuse, and A and B for the legs. Right triangles can vary greatly in the relative lengths of the sides, as well as the sizes of the angles that are not the right angle, but all satisfy the Pythagorean theorem. The sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse. Let's take a closer look at the unique properties of right triangles, including the Pythagorean theorem. From buildings to bridges, right triangles are a basic and often essential component of engineering and architecture. Architects use right triangles to construct skyscrapers, landmarks, and more. Let's take a look at two types of right triangles that have some interesting properties. What makes them special is based on the angle measurements of the non-right angles. One, the 30-60-90 triangle, has angles measuring, you guessed it, 30 degrees, 60 degrees, and 90 degrees. In this triangle, the length of the side opposite the 30-degree angle is always exactly half as long as the hypotenuse. You can see how this makes sense because it's half of an equilateral triangle, which has all angles of 60 degrees. If the hypotenuse of this triangle is 8, then the side opposite the 30-degree angle must be 4. Here's another special feature based on the Pythagorean theorem. The length of the side opposite the 60-degree angle is always the product of the length of the side opposite the 30-degree angle and the square root of 3. Like this. You could also state the property this way. The side opposite the 60-degree angle is always the product of 1/2 the hypotenuse and the square root of 3. No matter what size the triangle is, as long as its angles are 30 degrees, 60 degrees, and 90 degrees, these properties hold true. Another special right triangle has angles measuring 45 degrees, 45 degrees, and 90 degrees. Since the triangle has two congruent angles, this type of right triangle is also an isosceles triangle. In an isosceles right triangle, the legs are always congruent, and the length of the hypotenuse is always the product of the length of a leg and the square root of 2. If a right triangle with angle measures 45 degrees, and 90 degrees has two legs of length 9, then the hypotenuse must have the length of 9 times the square root of 2, or about 12.7. Another interesting type of right triangle has whole numbers as the lengths for all three sides. These sets of 3 lengths are called Pythagorean triples. One common example of a Pythagorean triple is the 3-4-5 triangle, which has sides of length 3, 4, and 5 units. Like all right triangles, Pythagorean triples must satisfy the equation a squared plus b squared equals c squared. The cool thing about Pythagorean triples is that they come in families. Let's take the 3-4-5 triangle, for example. If we multiplied each side by 2, we would still have a right triangle. Let's show how 6, 8, 10 also satisfies the Pythagorean triple. Here are some other families of Pythagorean triples. These special types of right triangles all have unique properties, but remember, all right triangles satisfy the Pythagorean theorem. Between the years of 580 and 500 BC, a mathematician by the name of Pythagoras proved that the square of the length of the hypotenuse of a right triangle is equal to the sum of the squares of the lengths of the other two sides. But believe it or not, Pythagoras was not the first person to figure out that a squared plus b squared equals c squared. Ancient clay tablets show that the Babylonians in the 2nd millennium BC, 1,000 years before Pythagoras, understood the relationships among the sides of a right triangle. But Pythagoras got his name on the theorem because he was the first to prove it. Let's look at a proof of the Pythagorean theorem using geometry. To start the proof, first construct a square on each side of the right triangle. The length of one of the sides of the triangle squared is exactly the same as the area of its corresponding square. Why? Because, remember, the area of a square is the length of its side squared. Now, from this structure, draw a line extending the A side and a line extending the B side. Then draw two lines perpendicular to these lines so that the blue square is surrounded by a larger square. Each side has the length A plus B because the surrounding triangles are congruent to the original one with side lengths A and B. From that, you can then conclude that the area of the larger square outside the blue square equals A plus B squared, which can be rewritten A squared plus 2AB plus B squared. Now the blue square is surrounded by 4 right triangles. The area of each of these triangles is 1/2 A times B, making the area of all 4 triangles together 4 times 1/2 A times B, which is 2 times A times B. You can see that the area of the blue square is the area of the large square minus the areas of the 4 triangles surrounding the blue square. Here's the equation. C squared equals A squared plus 2AB plus B squared minus 2AB. 2AB minus 2AB is 0, so C squared equals A squared plus B squared, which can be stated as the area of the blue square equals the area of the green square plus the area of the red square. This equation looks familiar, doesn't it? Congratulations! We've now followed one of many possible proofs of the Pythagorean theorem. Architects and carpenters constantly rely on the stability of right triangles in the construction of buildings. This means they also can rely on the Pythagorean theorem when it comes to measuring them. This theorem states that the square of the length of the hypotenuse of a right triangle is equal to the sum of the squares of the lengths of its legs. Because it expresses an algebraic relationship among the lengths of the sides of right triangles, the Pythagorean theorem can also be used as a formula to calculate the unknown length of any side of a right triangle when the lengths of the other 2 sides are known. This carpenter is constructing the framework of a house. He needs to install a diagonal support beam between 2 perpendicular boards. The 2 boards form 2 legs of a right triangle, measuring 4 feet and 6 feet respectively. The carpenter needs to know what length to use for the diagonal support beam. He needs to find the length of the hypotenuse of the right triangle, with these 2 boards forming the legs. Remember, the 2 legs measure 4 feet and 6 feet. He can substitute these lengths in the formula A squared plus B squared equals C squared and solve for C. He needs a board about 7.2 feet long, or about 7 feet 2.4 inches. Now, say the carpenter already knows the length of the triangle's hypotenuse and the length of one of the legs, but needs to find out the length of the other leg. He can still use the Pythagorean theorem. He just rearranges the equation. Here's an example. If the hypotenuse has a length of 10 and one leg has a length of 9, he would rework the equation like this. He'd substitute the numbers and then solve for B. The answer? Side B has a length in feet of the square root of 19, or 4.36. Problem solved.